All right, so today we are going to address another type of the chi-square distribution. It's called test for goodness of fit. And the way you recognize test for goodness of fit is to, number one, understand that you're dealing with one variable. So you don't have a two-way table. You have one obviously categorical variable. And you want to know if it has a specified distribution in the population of interest. That's how you recognize this type of tests, chi-square tests. So I'm going to work out an example, and I made it simple in a sense that my category doesn't have like 5 columns. I just made a 2-column one. So suppose that you found in a group of, let's say, 40 students at your school, that 10 of them are left-handed. And I actually went online to see what is the percentage of the population that is left-handed, and I found that it is 13%. That's something I just did, okay? So the theory out there is that 13% of the population are left-handed, and therefore 87% are not. And you were curious, and you took a group of 40 students, let's say, and you asked them, and 10 of them said that they are left-handed, which means 30 of them are right-handed, okay? So the table, don't let this table deceive you. This is not a two-way table. This is a one-way table, okay? Why? Pretend the expected values here that I wrote before I began to speak are not there. So you basically have left-handed, and right-handed. You have 10 and you have 30. That's it. Okay? So you have one categorical variable, not more. And I put it horizontally just to keep my life easy. And we are going to follow the same procedure, but don't just stop watching, because even though the skeleton is the same as the one we did for the test for association, a lot of things are different. For one, there is only one variable. So degrees of freedom, if you remember, was okay? It was number of rows minus 1 times the number of columns minus 1. Well, that doesn't make sense anymore. So make sure you pay attention to this discussion, okay? So how do you find, if this theory is correct, if this theory that 13% of the population are left-handed, what do you expect out of 40 people? Well, we expect that 13% of them to be left-handed. Well, 0.13 times 40 gave me 5.2. And of course, you expect 87% of 40, something happened here, of 40 to be right-handed. You can do it differently. Since you know your total is 40, and you already found out that 5% is expected to be left-handed, well, 40 minus 5.2 should also give you 34.8, okay? So this is a one-way table, okay? So I found the expected values because there are very few. It's easy for me to figure that out. And now we are going to begin. So we are running a test, not a confidence interval. So H null would mean that 13% of people are left-handed, and the alternative hypothesis would say, no, it's not. It's not left-handed. So the alternative hypothesis says the theory that 13% are left-handed is incorrect. Okay? Make sure you locate yourself. This is always helpful, because then you'll know what to do on the calculator, okay? You need to know where you are. This is a test for goodness of fit. That's what it is, okay? It is a test for goodness of fit. Step 2, we check the conditions. They are exactly the same. So we want to know how that sample of 40 was taken. I didn't describe it, but that's something you want to address. And don't just write things like this. SRS, check. This is not a way to test this condition, okay? Make sure you put some effort in it. The large counts, we want to make sure that all expected values are at least 5. If you go back here, we found 5.2. It's close. Carrying is close, and 34.8, which is much bigger than 5. Okay, so that condition is checked. And then the 10% condition, you want to make sure that the population is at least 10 times of the sample size. We're assuming that the population is at least 400, right? So I'm not worried, especially if you're looking at all students in the US. We definitely have more than 400, okay? Then we are going to begin the calculation. I'm going to do it by hand, and then I'll show you how to do it on a calculator in 2 ways. Recall the chi-squared value. This is called the test statistic, okay? The test statistic is the sum of the observed minus, I don't know what happened to me, I'm missing pieces, minus expected squared, so it doesn't matter which one you subtract from the other. Once you square opposite numbers, you get the same value, divided by the expected value, and then you apply the sum. So you don't just apply the sum to the top, you apply the sum to this whole thing. Because I only had 2 numbers, I did it by hand. So it's 10 observed minus the corresponding expected. Go back here. Observed minus the corresponding expected. You don't do this minus that, for instance. Squared divided by the expected value. Those 2 numbers have to be the same. Plus the second one, 30 minus 34.8 squared over that. It gave me this plus that. And I got 5.092. So that is the chi-squared value. Then to find the p-value, and I'm going to show it to you in 2 ways. One way is to go to distribution, okay? Second vars, which is distribution. If you recall how we found norm CDF, norm PDF, binom CDF, binom PDF, geometric, all of those distribution. You scroll down to number 8 until you find chi-squared CDF, not PDF. CDF stands for cumulative. CDF refers to cumulative density function, and PDF stands for my goodness, I forgot. So it'll come back to me. So why cumulative? Because you're not writing an equal sign, you are accumulating areas. Okay, anytime you have more than or less than or greater or equal to or less than or equal to, you do cumulative density function. The parameters that you enter here are the interval and your degrees of freedom. Okay, so we write 5.092. That's the right hand side value. Okay, so I'll draw a picture in a second. The upper limit is a large number. I tend to write 10 to the 8, and degrees of freedom here is going to be 1. All you have to do is n minus 1. That's all you have to do in this example. And it makes sense, it should make sense to you. So n is 2, and 2 minus 1 is 1. Why is it 1? Because, go back to, if I'm given this piece of information, okay, I am interviewing 40 people, and 10 of them tell me that they are left-handed, I don't need 2 degrees of freedom. Since I know 10, I automatically know 30. So you need 1 piece of information. That's all you need. That's how you find the degrees of freedom. So it's n minus 1, which is 1. So I put that in here. So interval and degrees of freedom. And I got this p-value, which is fairly small. Not extremely small, but it's definitely small than let's say significance level alpha equals 0.05. When the significance level is not given to you, and I didn't give you one, you just assume, just write it down and just say assume, okay? So if we assume that the significance level is 0.05, clearly alpha is much bigger than the p-value. So the p-value is less than alpha, which means we are going to reject H null. We have evidence against H null. That is, the theory observed to be invalid, which means the percentage of the left-handed people is not 13%. Let me draw a quick picture for you. You may recall that the chi-square distribution is not normal. It's not even symmetric. It is extremely skewed to the right, and it looks something like this. Okay. Now, when degrees of freedom, when n is 2, like in our case, which means df is 1, it actually breaks apart from the origin. It looks like 1 over x, kind of. Okay. That's the only time you see the chi-square distribution looking the way it looks. It looks like 1 over x. It's not 1 over x, but it looks like it. So basically we have, I'm going to go to the right. Okay, I don't have much space. Basically, your cutoff is 5%, okay? That is your cutoff. This area is your cutoff in blue. And your p-value turned out to be very small, which means, and p-value is an area. So your p-value is here, right? Which basically means that you actually crossed the cutoff because your red area is much smaller than the blue area, including the red area. The blue does include the red, okay, but the red does not include the blue. So that's one way to interpret this. Now, every time you cross over, you are far away from where chi-squared equals 0, right there, which means H null is true. You cross over. If you don't cross over, if your p-value is here, that means you didn't cross over, which means you don't have evidence to reject H null. It's kind of a double negation. You do not have evidence to reject H null. Now we have evidence to reject H null because we cross over. And oftentimes we always compare areas, always, right? You see it in the books. You always compare the p-value to the significance level. Sometimes it's good to compare locations. In other words, what is this location reflecting 5%? And what is this location reflecting the p-value? And that's what I want to do next, just so that you know how to do it. How do we figure out the area reflecting 5%, which is the blue area? How do we know this particular location, this chi-squared value right there? How do we know? It's easy. You can go to the book. My degrees of freedom is 1, okay? And read this, the p-value to the points chi-squared with probability p lying to its right. So if this was alpha, 5%, we want to know what is this cutoff location. That cutoff location has to be 3.84. 5% to the right, that's 5%. Degrees of freedom is 1. So the chi-squared cutoff is 3.84, okay? Okay, so since my cutoff is 3.84, and my chi-squared was found to be 5.092 earlier, I don't have to find a p-value at all. I could just compare this location to this location. Now, this location is definitely bigger. So if we go back to the picture, my cutoff location is 3.84. My chi-squared test is actually right there. That is 5.092, and this location is 3.84. Once again, I cross over. It doesn't matter. You can compare location to location, or you can compare area to area. So since our cutoff location is bigger than this sorry, this is the cutoff location. Since our chi-square test is bigger than the cutoff location, we would reject H null again and make sure you write it in context like I did here, okay? So I just didn't want to write it again. So now, we're kind of done. But I want to show you a couple of things that I think will be helpful to you. So, number one, I want to show you how to do this again and not do it by hand. And you might say, well, I know we did that last time. No, actually we didn't. Because we have to, last time we used matrices to compute chi-squared value and the p-value. Well, we don't have matrices. This is not test for association. This is test for goodness of fit. We have one column. You're not going to be able to use matrices, okay? So here is how you do it. You go to stat edit. Under L1, you basically write your observed values. I think we have 10 and 30. Under L2, you write the expected values, whatever we got. 5.2 and 34.8. 5.2 and 34.8. So you put your, you fill your tables under L1 and L2. You go to stats, tests. You go to letter D. It's called goodness of fit test. That's how it looks on the TI. And you click on it, and you're going to get this table, okay? You're going to get L1. Yes, that's what you wanted. You wanted the observed under L1. You have L2, of course. You write 1 for your degrees of freedom. It's 2 minus 1, which is 1. And you click on calculate, and I'll come back to this in a second. Once you click on calculate, you're going to get this chi-squared value for free, which we computed by hand here. Okay, you don't have to. And you also get the p-value. Okay, which also I showed you how to do it by hand, on the calculator in a different way. So there is one way, and here is the other way. You just get it for free. Okay, so that's how you would find step 3. Step 3 is always the calculation. This whole thing here, you could do it in a different way. Now, you can go back again and click on draw, and you're gonna get a picture just like I mentioned earlier. It should look something like this. In our case, it should look something like this, because it recognizes that degrees of freedom is 1. So it's gonna look like 1 over x. Okay, and it's gonna shade your 5% significance level. It's gonna shade it for you. So if you want to visualize this, you could just click. After you calculate, go back here again, and go through these and click on draw. Now, at the bottom, you see CNTRB, and you really don't need to know this at all, but just in case you're curious, these are the contributions of these values. The contributions of these values to the chi-squared value. What is each of those? In other words, which of these contributed more than the other? And I can tell very quickly. I mean, if you say 5.2 is far from 10 and 34.8 is not that far from 30, I would agree with you, right? And that's the contribution here. So the first contribution to this value of 5, I'll repeat here. See this number here? How much of these two expected values contributed to the 5.092? And just to the naked eye, we knew this contributed a lot less than this one. And if you look at these, the first one contributed 4.43076, and the second one contributed almost nothing, 0.662. And if you add these two, you should get 5.092. You really don't need to know this, but I thought in case you're curious, you see it, you should be able to get it. Now, some students will do this, okay? They'll go to stat tests and they will not see test for goodness of fit. If you have a TI 83 or 82, whatever, you're not going to see this, which means you're not going to be able to do this. So quickly, how do you do it? Remember what we did earlier. We went to L1, we put our observed values, and we went to L2 and we put our expected values. I don't remember what they are, but let's just write expected values. Okay, you remember those. You can actually calculate this by going to L3. So you click on L3, so you have a blank table. You actually go up and click on it, and you write observed minus expected squared over expected. So you literally type L1 minus L2 squared. Now, if you do L2 minus L1 squared, that's going to be the same, right? Because if this number here is, let's say, 5, and this number is going to have to be negative 5, and once you square them, you're still going to get the same value, right? So these are opposite numbers, and if you square them, you get the same value. So it doesn't matter which one you start with first. So that's going to allow you to get values here. You're going to get one value here and one value here. And oftentimes, my table is very long, okay? So it's going to give you all of those values. But in this case, it's just going to give you 2 of them. And what do you need to do? You have to add them up, because the chi-squared is the sum of this stuff, isn't it? So there are 2 ways to add them up. You can go to stats, and then I think you go to list. Let me click. I have a calculator next to me. Stats, and then I go to, second stats. You go to second stats, which is list. And you go to math. You go to math. And then you go to number 5, which is the sum. And you write sum of L3 on the home screen, and it should give you 5.092. Okay, so that's one way to do it. Another way to do it is to go to one var stats, go to stats. Okay, I'll erase this. So you enter your L1, L2, okay? You go to stats, calc, go to stats, calc, which means calculates. You click on one var stats. And when I click on one var stats, it'll you find the sum, right? Let me try it. Should have done this before I got here. So let's edit. I have L1, L2, and then I go stats, calc, one of our stats. You click on L3. No, sorry. You go to you find the sum, the sum of L3 basically, which you already have, and it should give you the chi-squared value. Sorry if I'm a little disoriented or sloppy. I just thought maybe some of you may not necessarily have the TI-84 or something, or 83. I don't think the TI-83 gives you this, so that's why I want to mention it. So I hope this is helpful. Sorry for taking long, and have a wonderful long weekend.